Check it out now, y'all.
nanoHUB-U online instruction.
Today we're going to talk about the solutions to homework 4. Let's start with question 1. The homework says derive a relationship for the critical thermodynamic radius of nucleation of an electrodeposit lithium nucleus that also includes the effect of compressive stress Sp. Okay, and in this case, well, we can look at the total free energy of the system. In general or conceptually, you have a volumetric contribution where you account for the Gibbs free energy of formation, okay, plus the contribution from the overpotential, okay, plus an contribution from creating area in the system times the surface tension, okay. Conceptually, this goes or is proportional to 4/3 pi r cubed. There is, of course, a shape factor, a volumetric shape factor that one has to include there in order to get the right shape. And same here, this one there's a pi r squared proportional to this to the square of the size, and there's also, of course, an area contribution there. Okay. Also conceptually, as we go along, one can have, let's draw it here, the free energy, the total free energy as a function of radius. Okay, if I draw that, okay, the volumetric contributions, if delta G is negative, basically if the material indeed wants to transform, it'll go something like that. This goes basically as r cubed, okay, while this one over there, the area contribution will go proportional to r squared, so that the total contribution of the system will be the sum of both. So at the beginning, neither of them dominate. The area, because it goes as r squared, takes off first, okay, and then the volumetric eventually catches up until it comes down. Okay, the critical size corresponds to the size of this hump. This is RC or R star. Okay, and the energy barrier, okay, corresponds to the size of that hump, is the critical free energy. Okay, and well, if you go over the steps in the absence of mechanical stress, really that value corresponds to minimizing or maximizing that function, and that goes by doing something along these lines where you basically calculate the extremum, okay? And if you do that, okay, and let's revert back to black. If you do that, you will find that the critical radius goes as 2 gamma omega over ZF eta plus delta G. Let's see if I got that one right. This is something we have already done in class. Oh, there's an omega missing here. Okay, we did this already. Okay, and the relationship is such that when we make this overpotential more negative, we basically make this contribution come further down like this, as eta becomes more negative. Okay, and when you do that, then the energy barrier comes down and the critical radius basically starts going in that direction. Basically, we favor the nucleation of that phase. Okay, when we add pressure in the system, what we're saying here is that we're adding a P term in there, right, that we add to the system. Okay, that pressure has units of energy per unit volume. Okay, and what you can do is you can think that you are replacing delta GF with delta GF plus P. Okay, and everything we've done here still applies. Okay, so then in that case the solution following the same steps, okay, corresponds to then RC equal to 2 gamma omega over ZF eta plus delta GF, delta GF plus P omega, okay? And that's the answer to the problem. Okay, I took the easy path, which is basically acknowledge that either substituting that corresponds to basically shifting the free energy by an amount P, but you could have equally solved this problem by simply substituting it and then just follow the same steps we've done before and get to the same answer, okay? If you do that, of course, the answer then becomes D, okay, which is effectively what I wrote there, okay? If you go to question 2, which is, will the critical angle and critical radius increase, decrease, or remain the same with compressive stress? Okay, as you increase the compressive stress, what it will do, okay, is it'll actually make this free energy larger. Basically, you not only have to overcome the surface tension, okay, you will also have to overcome the stress that you're imposing on the system, effectively shifting the radius to the right and making this barrier larger. So therefore, the answer will be B, will increase in size. You have to actually have a larger nucleus that overcomes that barrier in order to grow. Question 3 is, will the critical free energy increase or decrease with compressive stress? And the answer is will increase in size. Will be the compressive stress will have to be actually increases that energy barrier. So that will be the improved one. And well, you can see why many people have aimed to make batteries that are mechanically compressed, because that at least delays the formation of dendrites. And well, in this case, in many cases, just by encapsulating the batteries, it's enough to add that additional component which will delay the formation of dendrites. Okay. Question number 4. For the cases where the driving force for plating is very small compared to the thermal energy, what is the dendrite radius as a function of time if you include the effect of stress on the following cases? And in this case, question 4.1 is for a flat surface and non-zero overpotential. Okay, so the first argument for the question is we're saying that the electrical energy divided by the thermal energy is a small number. Is basically we're saying that ZF eta over RT is much smaller than 1. Okay. In fact, we're saying that effectively this whole term over here is smaller than 1, much smaller than 1. So therefore, the deposition rate, in this case, equation 1 that you see up there, really can be reduced to an equation of this form. We can basically expand the hyperbolic sign to a much more linearized, convenient form, where we have J naught times 1/2 times ZF eta over RT plus 2 gamma omega over RT. Okay, and for the first question, the thought is that for a flat surface and a non-zero overpotential, meaning that this term R is so large, but so large that 1 over R basically can be ignored. Okay, that's the expectation. And if you do that, we know that gamma is effectively 1 over the molar volume times the velocity of the interface, or if you prefer, it's 1 over omega times dr dt, which is equal to all of that. Okay, and if you do that, and again, here we're just basically rehashing what we've done in class, but if we do that, it goes like this. You get a J naught over 2 ZF eta over RT, okay? And then from there, we can calculate the solution as we did it during class, okay? And if we want to include the effect of stress, basically we have to come back here and if you rederive this equation, you will find that the pressure which basically is the 2 gamma over R, you can substitute that by a generalized pressure times omega over RT, okay, which you can definitely add there. So this problem basically will look more like this. Okay, and notice that on the right side there's nothing depending on R, so we can readily integrate this, and we have that R is going to be equal to R naught plus J naught over 2 ZF eta over RT plus P omega over RT times T minus T naught. If we assume that at T equals 0, or T equal T naught, R equals 0, then we can get rid of these two, and then that allows us to pick basically answer B as the correct answer, right? So that's the answer of the problem. Okay, if you do that, we can then proceed to question 4.2. The question is, for a flat surface and non-zero overpotential, will the electrode deposit grow faster or slower or at the same rate? Okay, and in this case, since we have a non-zero overpotential on a flat surface, which corresponds to this situation, because the pressure is actually slowing, the pressure is basically suppressing the growth rate, we can say that that dendrite will be growing much slower than if there is no pressure. So that will make basically answer A to be the correct answer. Okay. Now we can go to question 4.3. In this case, question 4.3 says, for a flat surface and zero overpotential, basically what would be in this case the growth rate? And for that case, and let me erase this bit. Okay, this situation still applies, so I'm gonna revert here. Okay, when we have a zero stress and a non-zero overpotential, basically we have to refer to the general solution. Okay, and you can see the general solution has a very complicated form where we have W in this case is the log product function as we discussed it in class, and as compared to before where basically the surface tension is the one controlling the system. In this case, we don't have the radius or the overpotential. In this case, this relationship, equation 1, reduces to well, sorry, instead of having that, now we have okay, because now we have a different type of surface, right? Plus, in this case, P omega over RT, okay? Basically, now we have that driving force. So basically, this term over here is analogous to that term over there, okay? And basically, everything else follows, right? We can just substitute directly P omega over RT by 2 gamma omega over RRT. And so we will have to remap this equation and basically replace this whole term over here, okay, with the right contribution, right? And if you do that for every single contribution here, whoops, okay, as you go along, okay, you just go and replace all of these terms that we can identify, okay, then we will find that for that case, the answer corresponds to A, okay, that I'm not going to write down because it will take a long time to write. But effectively, we have substitute the effect of the overpotential by the effect of pressure itself. Okay, now pressure is the one driving the system for growing the structure. If we now use this argument for question 4.4, the question being for a curved surface and zero overpotential, will the electrode deposit grow faster, slower, okay, or at the same rate? And in this case, it'll grow, if you have a curved surface, it'll grow at a slower rate Why? Because now the pressure that we substituted here is actually the one controlling the growth of the structure. So in both cases, having a flat surface or a curved surface, it is expected that the stress will actually contribute an additional counter-driving force for controlling the system. Okay, thank you.